Alright, today we're going to be solving quadratic equations with complex coefficients. So for the most part, we've been solving equations with real coefficients. However, when the coefficients of z are complex, the process is a tad different. Now, our normal methods actually will still work. So the method that you see in the red box will still work, but it's going to be a bit more complicated. So if we just remind ourselves how to solve this, we can say x squared minus y squared equals 3, and 2xy equals 4. And if we solve that, we get y is equal to 2 on x, which means x squared minus 4 on x squared equals 3, which means we've got x to the power of 4 minus 3x squared minus 4 equals 0. And if we factorize that, we get x squared minus 4, x squared plus 1 equals 0. Now we know x has to belong to the real numbers, so that means x has to be plus or minus 2. Now we know that y is 2 on x, so y is plus or minus 1. I'm going very fast through that because there's already a whole video on this example. So this is plus or minus 2 plus I. Now that's all well and good, but there is a much faster way of doing this. Now this method will always work, and I always draw back upon it. And these formulas are very easy to remember, but it's not as easy when the coefficients are more complex and we have to use the quadratic formula, for example. So another method is this method here. Now it's not in many textbooks. I know it's in Steve Howard's textbook, but I think that's potentially the only one that has it. So for a complex number z, its square root a plus ib follows, as a is the square root of the modulus of z plus rez on 2, and b is plus or minus the sine of y, so whatever the sign, whether it's plus or minus of the imaginary component, multiplied by root z minus rez on 2. Now let's do the same question using that way. The modulus of that complex number is 5, that's a famous triad. So a is going to be the square root of the modulus, and then it says plus the real component over 2. 5 plus 3 is 8 divided 2 is 4, so plus or minus 2. And then b is the sine of y plus or minus the sine of y. Well, the sine of y is a positive, so we can just leave that there, plus or minus the square root of the modulus minus the real component over 2. 5 minus 3 is 2, divide 2 is 1, so plus or minus 1. So our answer is plus or minus 2 plus or minus 1i, which I believe we got up here. Yep. And we can say that this is plus or minus 2 plus I. Okay. Now we can use that to solve this equation here, which is going to be a bit more complicated. If we use the quadratic formula, we get minus 2 plus or minus the square root of 4 minus 4 times I. 4 times 1 times I. Now we can take out a factor of 2. So minus 2 plus or minus 2 root 1 minus I, all over 2, which is minus 1 plus or minus root 1 minus I. And if we use our new formula, well, we've got a equals the square root of the modulus of z, which is root 2. So root 2 plus the real component of 1 over 2. And then b is plus or minus the sine of y. Now the sine of y is now negative, so it changes the plus or minus to a minus plus. The square root of the modulus minus the real component over 2. So the square root of 1 minus I, quite a complicated square root, is plus or minus the square root of 2 plus 1 over 2 minus plus the square root of root 2 minus 1 on 2, which we could write as plus or minus, big bracket, root 2 plus 1 on 2 minus the square root of root 2 minus 1 on 2. And then if we actually solve this equation, we originally had this, and we're going to replace our square root with what we figured it out to be. So z is minus 1 plus or minus the square root, plus or minus root 2 plus 1 over 2 minus big square root 2 minus 1 on 2. Now, you theoretically could have solved this question the other way, but it would have taken you a very long time and you might not have got to a nice simplified answer like I've got. Alright, thanks for watching.